In this video we're going to look at the percentage yield and the percentage purity of chemical reactions. Now, when we do calculations in a class, we assume that all the reactants react, or all the products remain in the system. But in reality this isn't the case. Sometimes we find that not all the reactants fully react, that some of the product is left behind in the solution, or that some reactants or products are lost along the way. So we are going to look at how to calculate this in a quantitative way, and it's a very simple formula that we use. We can say that the percentage yield is the actual amount of product produced over the theoretical amount of product predicted times by 100%. So when we refer to amount, more often than not we're going to be looking at the mass in grams that is produced, but one could also use moles, and one could even use the volume of a gas product. So let's consider the following problem. According to the balanced chemical equation below, 21,9 grams of boron fluoride, this is boron fluoride, BF3, reacts with 25.6 grams of water, and it produces these two products, H3BO3 and HBF4. Now, I would like to give you opportunity to do this problem on your own, but I do want to draw your attention to the following. Note that in the problem statement that a quantity for the one reactant and a quantity for the other reactant are given. And as soon as this happens, you must be aware, alarm bells must go off, that you are more than likely dealing with a limiting reagent problem as well. So in carrying out the solution to this problem, please consider the fact that there is a limiting reagent in this problem. So question 4 asks, what is the maximum amount of HBF4 that can form? So in essence what is being asked is, what is the theoretical yield of HBF4? So in order to work this out, we are going to work with the balanced chemical equation, which states that 4 molecules of BF3 need to react with 3 molecules of H2O to produce H3BO3 plus 3 HBF4. So what's very important here is the molar ratio between the BF3, the water, and the HBF4. So these coefficients 4, 3, 3 are very important. We are told that the mass of boron fluoride is 21,9 grams. So this mass, boron fluoride, is 21,9 grams, and the mass of water is 25,6 grams. Now, the coefficients in the balanced chemical equation give us the molar ratio. So one of the key concepts in this section of work is the mole concept. So I'd ask you to please pause the video and convert both these quantities into the number of moles for each of these two substances. So to convert the mass of boron fluoride to the number of moles of boron fluoride, we use the formula little n equals little m over big M. Number of moles is mass of sample over the molar mass of the substance. 21,9 grams of boron fluoride divided by the molar mass, 11 for boron and for fluorine 19 times 3, because it's F3, gives us a molar mass for BF3 of 68 grams per mole. 21,9 grams divided by 68 grams per mole gives us 0.322 moles. Note that I've kept the third decimal place because eventually we're going to round off to the second decimal place. For the water, it's the same formula. Number of moles of water is the mass of the water sample over the molar mass of water, which happens to be 18 grams per mole. 25,6 divided by 18 is 1,422 moles. Now, in order to work out the yield of HBF4 with 0,3322 moles of BF3 and 1,422 moles of H2O, we now need to work with the limiting reagent or limiting reactant approach. We need to work out which one of these substances is the limiting reactant. So question B, what is the limiting reactant in this reaction? Justify your answer by referring to the calculations. You actually need to do this in part A as well. So what we're going to do now is we are going to use the molar ratio of the reactants of 4:3 to see which of the scenarios actually works out. And by scenarios, we're going to first look at assuming boron fluoride to be fully used up, and then scenario 2 would be the water being fully used up, and then seeing which one of the scenarios works out, and hence we can then work out which one is the limiting reactant or reagent, and then what is the theoretical yield of HBF4. So I'm going to encourage you to pause the video now and just to give it a try before you see my solution. So the molar ratio between BF3 and H2O and HBF4 is 4 moles to 3 moles to 3 moles. The reason why we leave out one of the products is because we are focusing on HBF4 as we want to know what the percentage yield is for that particular product. Now, if we look at scenario 1, in scenario 1, we are going to assume that all of the boron fluoride is used up. So there is 0,322 moles of boron fluoride, and we're assuming that it is all going to be used up. Now, how much H2O will be needed? Now, if we look at the ratio of boron fluoride to water, we see that it's a 4:3 ratio. So to get the amount of moles of water, we would multiply by 3 and divide by 4. You see 4 moles times 3/4 gives us 3 moles. So we're going to multiply this by 3/4, and that gives us 0,242 moles of water that would be required to react fully with the 0,322 moles of boron fluoride. Now, do we have 0,242 moles of water? Well, in actual fact, we have a lot more than that. We have 1,422 moles of water. So this scenario will work, And you'll see that I use a little rectangle just to separate the reactants from the products. Now, if 0.242 moles of water reacts with 0.322 moles of boron fluoride, then the amount of HbF4 produced is going to be in a ratio of 3 moles to 3 moles with water, or 1:1. So that means that 0.242 moles of HbF4 would be produced. So this scenario definitely works. But for the sake of clarity on this method, we are going to look at scenario 2 as well. It's also going to enable us to identify what the limiting reagent is. So in scenario 2, we are going to assume that all the water is used up. Now, we have worked out that there is 1,422 moles of water in the reaction. We have that. Now, the ratio of water to BF3 is 3:4. So to go from water to BF3, we are going to multiply by 4 and divide by 3, because 3 times 4/3 gives us 4 moles. So multiplying by 4/3, 1,422 times 4/3 gives us 1,896 moles of boron fluoride that would be required to react fully with 1,422 moles of water. Now, the problem is that we don't have anywhere near that amount of boron fluoride to react with the water. So this scenario doesn't work. So what is the limiting reagent here? Well, we can see that boron fluoride is the limiting reagent because there's not enough boron fluoride to react with all the water. So this is going to be the limiting reactant is boron fluoride because of the fact that there isn't enough of it in order to fully react with the water. So scenario 2 points to the fact that the amount of HbF4 that is produced is 0.242 moles. We now need to convert this into mass. So mass is number of moles times molar mass, and this would be the molar mass of HbF4. The mass of HbF4 is 0.242 moles times the molar mass. So the molar mass would be, I'm just going to move this over, it's going to be 1 for hydrogen, 11 for boron, and fluorine is 19, but there are 4 fluorine, so times by 4, and that would obviously be grams per mole. So the mass of HbF4 would be 0.242 times the molar mass of HbF4, which is 88 grams per mole, and that gives us that the mass of HbF4 produced is 21,30 grams. So this is the theoretical yield of HbF4, which we will need in the next part of this problem to work out the percentage yield. So now if we look at the C question, it asks if 3,74 grams of HbF4 forms in this reaction, determine the percentage yield for the reaction. Now, the 3,74 grams is in actual fact the actual yield of HbF4. That's the actual amount of HbF4 produced. So if we write this as the mass actual as 3,74 grams, and carrying over from the previous calculation that the theoretical yield of the HbF4 was 21,3 grams. So this is the theoretical yield. Then we can work out the percentage yield. So that is mass actual over mass theoretical. And to make it a percentage, we times by 100%. So this is going to be 3,74 grams over 21,3 grams times 100%. This gives us 17.56% yield, 17.56, and you can see that that's a very low yield. So this is obviously was a very inefficient chemical reaction that was carried out. The next type of calculation we're going to look at is percentage purity. So if we have a sample of a particular substance, and that sample has a mass M sample, and we know that for the most part that sample is for a substance X, but there's an impurity inside, and that impurity we can represent little granules of the impurity Y. Let's call impurity Y. Then the mass of Y would be My, and the mass of X would be the mass of the sample minus the mass of Y. So this is obviously, there's an impurity in here, so it's not a pure sample. So if we want to work out the percentage purity, then we need to work out what is mass X of the pure substance, because this is mostly X, compared to the mass of the sample. So we are going to do a calculation in the next slide where we work out the percentage purity by taking the mass of the pure substance, which in this case was X, and dividing it by the mass of the sample, and to convert it to a percentage we times by 100%. So let's consider this problem. There is a 5,3 gram sample of impure sodium carbonate. So we can write down the mass of the sample is 5,3 grams, and it is treated with dilute hydrochloric acid, and in this reaction 896 cubic centimeters, so cubic centimeters is volume, so the volume of the CO2 produced is 896 cubic centimeters, and this was carried out at STP. Remember, STP is 0 degrees Celsius, 1 atmosphere of pressure, which is equal to 101.3 kilopascals. And the reason why that is given to us is so that we can work with the molar volume of gas, any gas, in this case it's CO2, as being 22,4 cubic decimeters for every mole of gas. So the first question they ask us is to balance the equation. Now, it's an important fundamental skill to do this, so I'm going to ask you to pause the video and to quickly do this for us. Thank you. So the balanced chemical equation is 1 Na2CO3 must react with 2 HCl's to produce 2 sodium chlorides and 1 CO2 plus 1 water. So that is the molar ratio. 1:2:2 1:1. So we are going to need this molar ratio in our molar calculations. So 5.2 asks how many moles of CO2 was produced. Now, it's important to note with these purity and impurity calculations that we start on the product side of the chemical equation, as opposed to when we worked with the percentage yield where we started on the reactant or reagent side. So here now we have the CO2 and we are given that the volume of CO2 is 896 cubic centimeters. So we want to work out the number of moles of CO2. So we are going to work with the number of moles of CO2 is the volume of the gas, CO2, over the molar volume. Now, it's critical to remember that you can only use this formula for gases. And because of the fact that this reaction is taking place at STP, the molar volume is 22,4 cubic decimeters per mole, and the volume that is produced of carbon dioxide is 896 cubic centimeters, and we have a problem. Can you see what the problem is? We have the volume of the gas in cubic centimeters, but the molar volume is in cubic decimeters per mole. So we need to convert this to cubic decimeters. So I ask you to pause the video and quickly do that. So 896 cubic centimeters needs to be divided by 1,000, because there are 1,000 cubic centimeters in 1 cubic decimeter. So that's going to give us 0.896 cubic decimeters. So now substituting it into here, we get 0.896 cubic decimeters over 22,4 cubic decimeters per mole, and that gives us 0.04 moles of carbon dioxide produced. Now, if we go back to the chemical equation, we can see that in order for this amount of CO2 to be produced, a certain amount of sodium carbonate had to react with a certain amount of hydrochloric acid. Now, we do not have a limiting reagent problem here because the amount of dilute hydrochloric acid is not specified. So we can assume that there was enough hydrochloric acid in order to react with all the sodium carbonate that is in this particular sample. So the next question, 5.3, asks what mass of sodium carbonate was reacted to produce this amount of carbon dioxide. So we have now moved from the right-hand side or the product side of the chemical equation now to the reactant side. So we are now going to use the molar ratio in order to determine how many moles of sodium carbonate was used in order to react with HCl to produce the amount of CO2 that we have here. I ask that you please pause the video and try and work this out. So using the molar ratio of sodium carbonate to carbon dioxide, using the balanced chemical equation, we see 1 mole is to 1 mole. I put this little rectangle around the colon purely to show you that that side is the product side and this side is the reactant side. We can see it's 1 is to 1. So therefore, if 0.04 moles of CO2 was produced, it would have required 0.04 moles of sodium carbonate to be reacted with HCl to produce the 0.04 moles of CO2. Now that we have the number of moles of sodium carbonate, we now can work out the mass of sodium carbonate that was present in the sample in order to produce the 0.04 moles of CO2. Please pause the video and try and calculate that. So the number of moles of sodium carbonate required is 0.04 moles. The mass would be the number of moles times the molar mass. The number of moles is 0.04 moles. The molar mass of sodium carbonate is 2 times 23 plus 12 for carbon plus 3 times 16 for oxygen, which gives us a molar mass of 106 grams per mole for sodium carbonate, times the 0.04 moles gives us 4,24 grams of sodium carbonate. Now, going back to the problem, we see that the original sample was 5,3 grams of sodium carbonate. So we can assume that whatever impurity is in that sample, in order to carry out this calculation, whatever is in that sample that's not sodium carbonate will not react with the HCl. So it would not produce any product. So now what we can do is we can say, well, this is in actual fact the amount of sodium carbonate present in that sample. So using that, we can now work out the percentage purity. So we can say that the percentage purity of sodium carbonate in that sample is the mass of sodium carbonate over the mass of the sample, which would obviously include the impurity, times by 100%. So moving that up, we can see that that would be 4,24 grams over the mass of the sample, which we know is 5,3 grams, times 100%. So that works out to 4,24 divided by 5,3 times by 100, and that gives us 80% purity. So the percentage impurity would just be 100% minus the percentage purity. So 100% minus 80% would give us 20%. So in that sample, 20% by mass of that sample is not sodium carbonate. So this is a way of solving problems that involve percentage purity and impurity. Just to recap, that you will be given a quantity of one of the products. You will invariably be given the mass of the sample, and then working backwards from the product side to the reactant side, you will work out how much of the pure reactant was required to produce whatever product you were given, and then relating that to the mass of the sample, you're then able to get the percentage as was done here. So I hope that this has helped you to gain an insight in how to solve percentage purity problems as well as percentage yield problems. For further practice on these two types of problems, I'm going to refer you to the Google Classroom, where further exercises will be given and solutions to these will be posted.